Welcome back to Intrendias. We're looking at price movement probability. We're calculating the probability distribution of a stock's price movement during a defined interval of time. So why might we be interested in understanding probability distribution? It can help improve risk, manage forecasting, and other benefits. So for improving risk, understanding a stock's return distribution helps assess risk. A stock with a wide distribution experiences high variance and thus price swings, or aka volatility. For forecasting, understanding the distribution enables traders to forecast the likelihood of a stock increasing or decreasing by X%. And some definitions that we would need to know for probability is mu, or the mean or average return of a stock. And then the sigma, or standard deviation, measures the variability in returns. This captures how much the return fluctuates around the average return, which is also known as risk or volatility. A higher sigma means higher risk, while the lower sigma means lower risk. So by the end of the video, we'll be able to calculate a probability distribution that looks similar to what you see here. Let's start by collecting some historic data for a ticker of interest. For example, we're going to look into Amazon stock, and we're going to create a data frame using the Yahoo Finance library to download historic Amazon data. We're going to use 10 years worth of data. That's plenty of data to work with. And we're going to do an interval uh, of 1 day. That's going to turn the data frame to a daily data frame of open, high, low, close volume data. Sweet. So now we're going to turn this daily data into a weekly data. So for example, let's say I want to start selling covered Amazon calls. I want to sell weekly Amazon calls to minimize the risk associated with time. And it's important for me to understand what the probability of Amazon increasing by X% would be so that I could manage my risk. So, for example, between two standard deviations, around 95% of the data lives between two standard deviations. So, for example, the probability of Amazon going up 5%, according to this chart, is very minimal, right? 95% of the data exists between, say, 4.5% and negative 4.5%. So the probability of Amazon going up 5% within a week is very, very low. It's very low to happen. So for me, as the person selling the covered call, I'm going to assert, hey, I'm only interested in taking up this much risk. So I don't want to be below two standard deviations of the mean. Therefore, a covered call that's 5% with a strike price that's 5% above the current price, I might be interested in that. My premium might be smaller, but I'm more comfortable with that risk. So this distribution would help with that risk management. So let's assume that scenario, and I want to look at weekly data to sell weekly covered calls. So I could resample the data frame from above, convert it into a weekly, and then aggregate the first close and last close values. Okay, so what does this do? Essentially, now we have the first and last close price for each week. So, for example, October 6th, that's a Sunday. And each of these dates in this new data frame are Sundays. But for that trading week, the first stock price was around $186 a share. So from here, we converted it into the first close and first last. However, this multi-index column is kind of tricky to work with. So we're going to convert those column names into something more traditional. So let's say start of week price and then end of week price. So now that we have that, we can have something that looks a bit more traditional, something that looks a bit more familiar. Now, we're going through this process of figuring out weekly data, but you might wonder, why even do that? Why not just go up here and change this to 5 days? Well, the problem with changing the interval to 5 days is that now I'm experiencing dates that are not Monday to Friday. So, for example, October 6th, or excuse me, October 2nd, that was a Wednesday. And then September 27th, that was a Friday. And then September 17th, 2024, that was a Tuesday, which is not really what I want, right? I want a Monday through Friday data frame, or rather, the first day of the trading week compared to the last day of the trading week. So that's why we're going through the process of weekly data. So bear with me. Now, I want to know what the first and last dates were in that week, just for historic purposes. So I'm going to say start of week. So we're going to take the weekly data. We're going to get the index, which is always a Sunday. And then we're going to offset that Sunday into Monday by taking the weekday is equal to 0. And then I'm going to add pd.offset b day of 0. And this is business day. So this ending statement here ensures that the start of the week is always a business day. And then I'm going to repeat the same thing for end of week. This provides me always with a business day. And then we're going to offset the index with the weekday 4, turning it into a Friday. So now that I have all that, now we see the start of the week price. For example, in 2024, October 12th, it was $16. By the end of the week, it was $15 a share. And the beginning of the week was 10:06. End of week was 10:10. So let's validate with a date that was much closer. For example, let's look at this week, September 29th. That was a Sunday. The beginning of the week, though, it was Monday, the 23rd, which is correct, start of week. And then Friday, September 27th, was the end of week, the last business day, aka the last business day. So this start of week, end of week columns seem to be appropriately capturing Monday through Friday. Now I want to look at the price change that we see, which is basically taking the end of week price, minusing it by the start of week price. So I'm just going to paste that in. We have end of week, that's your Y2 minus Y1. And then we're going to capture the percent change. So I'm going to call that percent change. And you have your weekly data. I want the price change. And that's going to be your weekly data with the start of the week price. Start of week price. Alrighty, so then we're going to take one last look and make sure everything comes over smoothly. So we're seeing 186.5 minus 186.33. And then if I were to go to September 30th, I will see that the close price was 18633. I scroll down here and that's correct, 18633. And then the last trading day this for this week was 10:04, and then the close price was 18650, and that's what we see here, 18650. So minus these two values and we get 17 cents, and then the percent change is 0.09% because we already multiplied it by 100. So this is already in percentage. So now we have the weekly start and end date along with the start and end closing price, the percent change for each week, and the price change per week. So we have a nice weekly data set here, Monday through Friday, to help us make decisions on selling, in this hypothetical scenario, covered calls. Now that we have a clean weekly data set, let's jump into plotting this probability distribution. So we're going to create a pandas series and we're going to call it percent changes and store the weekly data percent change. And we're going to drop, just in case, any nulls that might be in our data set. So drop NA. So what this series looks like, let's just print it out just to see what it looks like. We get a float 64 type, and we have a length of 522 entries. So that's a pretty good data set for our probability. We're going to start the histogram plot, and we can do that by creating a plot figure and then a seaborn histogram plot with the percent changes as the input. We're going to do bins of 30. You could increase the bins if you want to be more granular, but 30 to start off. And then this is going to be a density distribution. So we're going to fit a normal distribution to these percent changes for model simplicity. So as we mentioned, we have a mu and a sigma, and we're going to have these calculated for us when we fit a normal distribution onto the percent changes. It's worth noting that stock returns are sometimes usually not normally distributed. However, in financial modeling, a normal distribution is used for model simplicity and ease of use. So we could maybe one day look into right skewed models. But for now, we're going to normalize on a normal distribution here. So just to keep our code dynamic, I want to find the minimum x and the max x. And this will allow for the plot size to stay dynamic. So the plot x limit always ensures that the plot is of good size. So if a stock is only $10 a share, the x-axis will stay between $5 and $15 a share. But If a stock like Amazon is $180 a share, then your x-axis is going to reflect that. So we're going to use the x-min and x-max to keep a dynamic x-axis. The x here in NP dot lens space, this will create an array of 100 evenly spaced values between x min and x max, and the arrays x represent the range of x values over the fitted normal distribution will be plotted. So essentially this will represent our x-axis down here. So just for some context as to why I'm calculating these variables, we're going to have a variable called P, and this is going to be using the normal dot PDF. PDF stands for the probability density function for the normal distribution, so hence norm. And this is using the estimated mean and standard deviation over the range of x values that we just calculated. And the resulting P array represents the corresponding y values for the probability density function for the fitted normal distribution. So I'm going to feed the PDF the x array that we created along with the standard deviation and the mean. So mu and sigma. And now we're going to have a plot with x and p. And then the K represents the color of the line, which is black. And then the line width is just the line width. Okay, so here is what we currently have. We have the percent change. This is our x-axis. This represents the weekly percent return of, in our case, Amazon stock. And then the density. The density is the frequency of this return occurring. So we see that the tail gets a lot thinner on the right and left-hand side. This shows that Amazon going down, say, 10% is a very rare occurrence. This is probably well over, 2 standard deviations. So maybe on the flip side, you want to say, hey, I want to start selling puts on Amazon, right? If I sell puts on Amazon, I could collect premium on cash that's parked in, say, a brokerage account. And if I'm like, I'm happy to buy Amazon at a better price, but Amazon's kind of expensive right now. I'm willing to park aside some money, sell some puts, collect premium until Amazon comes down to a favorable price. And maybe, you don't want to get assigned. So you'll say, hey, I'm comfortable with a strike price that's 5% away from the current market value of Amazon. And -5 or -10, that'll provide you with some premium, but manage lower risk. So here's our probability distribution. And I'm trying to connect like a business case to why you would even want to do this, right? So let's continue on because I want to know where the mean is. I want to know where the standard deviation is. And I want to know where the second standard deviation is and see which percent changes are of low probability, right? So we can take advantage of PLT dot v line, so axis vertical line, and we're going to take the mean, make that the color red, and then line style, you could do anything you want here, but I'm going to do dashed, and then the line width, just so that we could read it, it's 2, and then plt dot show, just to see what we just did. So boom, now you have the mean in the dash red line. You could see that it's a bit above 0, so the average return from weekly Amazon is, say, about 0.2%. Now I also want to know where the standard deviation is. Where's the positive standard deviation? So we're going to do something similar. We're going to use vertical line, standard deviation plus sigma, and then use the color. In this case, let's just do green. Line style, do dashed. And then line width of 2. And I'm getting an error. That's upsetting. Module has no attribute. Oh, it's because I spelled it wrong? Yep, I did. Okay. So let's do plt.show, and then I could show you what we just did. So there you go. You added your positive standard deviation, and we see that a positive standard deviation of 1, standard deviation 1 is pretty close to a weekly percent return of 5%. So if I'm risk averse, I might say, hey, I want to sell covered calls that are at least, by minimum, at least 1 standard deviation away from the current price of Amazon. And I'll say, hey, the probability of Amazon going up more than 5% is above 1 standard deviation away from the mean. I'm pretty comfortable with that risk. I'll be on the winning side of that trade majority of the time, so I'm happy to sell that covered call. Okay, great. So we're going to repeat this process for the other standard deviations. And then if you perform these additional lines here, you'd finally get these standard deviation lines along with your mean. So like I mentioned earlier, Amazon dropping 10%, that's well above, or in this case below, the below 2 standard deviations from the mean. So if you're risk averse, you might want to sell that covered call. Quite frankly, if that covered call or put even exists, because that is pretty far. Okay, so next we're going to add lines or add labels for our lines because, someone might look at this and be like, what do these lines mean? I don't know what they mean. So we can perform some text labeling. plt.ylim, this is for location labeling. So where along the y-axis do you want this text? And then these labels, the mean, standard deviations, these labels are going to appear on the lines. So if I do that, boom, you get your mean, standard deviation 1, standard deviation 2. And then we can make this pretty. We can add a title, X label, traditional things like that. And then there you go. So for example, here, the weekly average Amazon return is around 0.44%. The standard deviation is 3.9. So for example, here, I want to sell an Amazon covered call and I want to ensure that the covered call that I sell is one standard deviation away from the mean. So, for example, uh, I'm going to look up how much data lives within one standard deviation. Because two standard deviations, it's about 95% of the data, and then around 68% of the data exists um, within one standard deviation. So from this green line to this green line, 68% of the data lives within this boundary. So then on top of that, you add the data that lives past the -1 standard deviation. Um, so you're on the winning side of that 5% change if you do sell a covered call on that. Okay. So from here to here, 68%. From here to here, that's about 95% of the data. And if you even added 3 standard deviations, 99.7% of the data lives um, within 3 standard deviations. So now this is where the uh, application comes in. So now I want to know the actual probability in terms of a percentage. What's the probability of Amazon going up 3% within a week? So let's say the threshold, this is my percent change. Let's say it's 3%. And I want to know what's the probability of Amazon going up 3% in a week. So I can use the probability, let's call a variable probability, and use the survival function, or this is also known as complementary cumulative distribution function for normal distributions. Uh, this provides what probability in terms of percent an event will happen. And we're going to have to feed this function some data. So it needs the threshold. This is the 3% that we want to know. And then we're going to enter the mean value, which is the mean of the standard deviation. So argument lock is equal to mu, and then scale is sigma. So this sets the standard deviation of the normal distribution. And then this probability variable will calculate the probability that a random value from the normal distribution with mean of mu and standard deviation of sigma is greater than the given threshold. So once I do that, let's make the output pretty. And I'm going to say the probability of Amazon stock going up more than 3% in 1 week is the probability times by 100. And then I'm going to round it to 1 decimal point, and then I'm going to turn it into a percentage. So here you go. The probability of Amazon stock going up more than 3% in 1 week is 25.6%. So that is decent odds, right? So 75% of the time you're on the winning side of this trade. You can sell the covered call, you could keep the premium, and then repeat it next week. However, 25% of the time, you could see Amazon increase in value more than 3%. So maybe you're a bit more risk averse. You're like, hey, I have 100 shares of Amazon, but I don't want to keep selling these covered calls and getting assigned and then missing out on potential capital gains. So let's say I'm a bit more risk averse. So I want to sell a covered call that's above one standard deviation, and I want to have a strike price that's 5% above the current price of Amazon. Now your odds are even greater, right? The probability of Amazon stock going up more than 5% in 1 week is 12%. So this is helpful because I could say, well, a strike price that's 3% above the current stock price on a Monday, I could collect more premium, but I'm not comfortable with 25% probability of getting assigned. But if I sell it at 5%, I'm only at 12% probability of getting assigned. My odds are a lot better. 25 is great, but 12 is even better. So this helps assess risk for an individual, um, and not just assessing risk for call options or put options, but also forecasting. You can input this probability distribution into a forecasting model, and the model would be able to understand that, hey, the probability of Amazon going up 5% based on historic data is only 12%. So maybe we should decrease the weight of Amazon going up 5% and favoring a better model, because again, the probability goes up only, or is up only 12%, if that makes sense. So you could change the ticker. For fun, let's just do Bitcoin to USD. I don't know. Let's do crypto. Um, so here you see a mean of 0.92, standard sigma of 8. So if you remember, I believe the sigma for Amazon was way lower, right? Amazon 3.9. So 3.9 for a tech company, right? But then if you go to Bitcoin, the sigma is even larger. It's now 8.5. So just from that value alone, we could tell, okay, Bitcoin is clearly a lot more volatile. You could probably tell from the chart itself, right? And then the probability of Bitcoin going up more than 5% in 1 week is 31%. So 1/3 of the time Bitcoin goes up more than 5% in 1 week, which was pretty good. And if you remember, Amazon's probability of going up more than 5% was about 12%, right? The probability of Amazon stock going up more than 5% was about 12%, but here it's 31%. So I hope this video was interesting. I hope me bringing in covered calls and puts, hopefully, I was trying to connect the coding to a business practice, because I want to ensure that there's some curiosity of like, well, why do we want to code this, right? So I'm trying to connect back to strategy that you might want to implement based on this code. So I hope you did find this video helpful. If you did, please subscribe and like the video, and comment down below what you thought was helpful, maybe what you think would have been better. I definitely love hearing the feedback, and I definitely love the engagement. So I appreciate the likes and the subscriptions. It does help, and it does mean the most. Very much appreciated. And I will get this code up on the blog. So as long as you have Intrendia's Essentials, which is a free subscription, you should be able to see this code on a blog post. So appreciate your time with me, coding with me today, and thank you so much for watching. Thank you for hanging out with me, and I will see you all in the next one.